Right. I know that lesson was that video, last video for the second part of the lesson was quite long. This video won't be nearly as long, but it's equally important because I want to continue the discussion about the Q macros program and the other models that are in there that are available for you to use. Now, these are classified in the following way. Researchers and mathematicians use and assume for all of these different tabs and the different inputs that the exponential distribution for the arrays. And the way that's indicated in a shorthand is to use this term M. So the first term in this symbol in this shorthand talks about the arrivals, and M actually stands for a mathematician's name who was Markov. And Markov was the mathematician who developed a lot of these models and a lot of these tools. So and from the strength and the power of the exponential distribution. So M stands for Markov and relates to the fact that the arrivals in this case have exponential distribution. And you'll see here for these next set of models, and grab a different color, that this indicates that the service rate, second column is has to do with the services. Let me go back. The first column has to indicate what the process is for the arrivals, and then the third column, get our green, is the number of servers. So this is the service process and the number of servers. That's this third index. So every one of these models has exponential arrivals. It does have infinite population and first come, first served. So if any of those are violated, you cannot use these tools. But the one that we use today, or in the earlier lesson, was that for multiple servers. That's the one that we use for the Draper Clinic. But there's also these that are available as well. If you need a single server, you can actually also type in S equals 1 in this model and it'll work, or you can use the single server model for our previous lesson, like with the Peachtree Airport. So I would encourage you to go back and look at the Peachtree Airport and see if you can identify all of the operating characteristics correctly from the Peachtree Airport. The one that we won't investigate, but it's there available for you, that some of you might need on a project or on another problem, is a situation where there's multiple servers, but the queue capacity is finite. So if I had gone back and said that the capacity for the Draper Clinic, there was only 10 seats available in the Draper Clinic, that would be the term that you would input for B, and it would produce the same operating characteristics using different formulas, however. And then the last two that we'll talk about that's available are deterministic services. And what does that mean? That means that deterministic means there is a fixed service time, but there's only one server. So in other words, it's a mechanical process that every customer has the same service and has exactly the same service time, but the customer arrivals are exponential. And then lastly, a general service distribution, which means that the services are random numbers, but you can describe what that distribution is. So those are the different capabilities of this Q macros software. So I would go and experiment with it and see what you can, just play around with it, see what you can learn. The other thing that I want to point out is that on page 216 of your textbook, There's also additional formulas. There's also the case where there's the single server. There's the case where there's multiple servers. But then there's the single server case with a finite calling population. And this is an interesting model. It's not that the line is limited. The queue, the waiting area is still infinite, but maybe there's only there's a fixed number of customers who are actually going to be using the system, and there's no more than that number. And then there's a single server with a finite queue length, but again, these are the manual. This is the same as one of the models in the queue macros, but this is, you would have to compute this by hand. And then there's a single server with a deterministic service times. Again, same as the model it's in queue macros, but you would have to compute this by hand. So all of those tools and resources are available. Now the next two slides, and really the last two slides that I'm going to talk about, are going to be new information that's not in your textbook. And one of the things that I want to point out is that students will tend to get confused in the situation where we have a multiple server case. In other words, again, remember, our multiple server has one line. And this is a bank teller where we've got two tellers working, or a bank inside from the bank. And again, this is evaluated as, just as we've seen and just as we've been doing with the Draper Clinic. This is the Draper Clinic problem. But this is the situation that's very, very different. But unfortunately, some students may try to analyze it the same. This is the case where we have two independent single servers. Each server has its own line. So in this case, there's line number one and then there's line number two. This is very, very different. This is not a multiple server situation. This is two single servers. The difference is, and the system on the left, which is like our Draper Clinic, the arrival rate is lambda. In the situation on the right, the arrival rate to each one of these lines, this again, I'm going to call this is the grocery store or Walmart or most department stores, where if there's the arrival rate of the customers will choose one of the two lines. And you can assume, by the way people behave, that over time the same rate of arrival will occur in each one of these lines. So the actual effective arrival rate for each one of these lines is lambda divided by 2. And we're going to evaluate this as two independent single server systems with these parameters, where we have a single server, the arrival rate is lambda over 2, and the service rate is mu. That service rate doesn't change because the servers provide the same service. Now, let's think for a minute. What would happen if we had what would happen if we had 3 of these? Again, we had 3 in our grocery store, or if we had 4 lines open. Well, in that case, in every case, if we had 4 lines open, we would still have there would be 4 independent. Each would be a single server with the arrival rate of lambda equal 4, or 3, or 5, or 6, or how many ever of these lines were open. Okay, but that's a very important distinction that I want you to make. Excuse me. And I would like for you to read through this, but there's one other important distinction. for the operating characteristics for the two independent single server case. When you're evaluating L or L sub Q, in other words, the number, this is the number of customers in the system, the number of customers, once you do this evaluation for this system, you're going to get an output of L, but that's going to be the number of customers just only in one of these systems. That would be, for example, just this system. So for the whole system, there would be L on average, L customers in this line and L customers in this line, and so on and so forth, no matter how many lines you had open. And so consequently, if there were two single servers, you would have to multiply L by 2. So the actual L effective is, for the system, if you will, is 2 times L. So it's twice the actual value of the single server. But the waiting times do not change, because the waiting time in this line will actually be the same as the waiting time in this line. So there's a little subtlety there in terms of how you do that, how you now analyze the outputs from those, from this, particularly from this situation where you have multiple, I'm going to call this a multiple independent single servers. Okay, hopefully that's clear. Think about that carefully. Now, the last thing we want to talk about is the cost of operating. We haven't really talked about this, but we do want to talk about this and give you a way to analyze how much it costs to operate a waiting line system. And the formula is fairly straightforward. There's some modifications that would occur to this, but we're going to calculate the total cost for operating the system, and it has two components: the cost of your servers and the cost of the customers that are in the system. And so there's 4 terms that we're going to use for this, whereas C sub S is the cost for each server, for their per hour cost, their hourly wage rate. S is the number of servers that are being used. C sub W is the cost for a customer waiting. A little bit hard to analyze or to grab, but you customers have a waiting cost. Think about the time that you're in the doctor's office waiting to see the doctor, what you could be doing, and how valuable your time. And then L in this term is just the average number of customers that are in the system for the system. So for example, let's think of our previous problem. Let's suppose our doctors, and we'll make the arithmetic easy, that each doctor is earning $100 per hour. We know from the previous problem we had 2 doctors. Our cost for customer waiting per unit of time, let's suppose it costs $25. Those customer, the average earning rate is $25 per hour. Maybe a little high, but in any case. And then L is the average number of customers that are in the system. And I don't know if you remember, but the average number of customers that were in the system in the previous slide was 4.8. You can go back on and check that on QMacros. So in order to calculate the total cost, so the total cost of this doctor's system with 3 doctors is 200 plus 25 times 4.8 and 25 times 4.8. I'm doing a little arithmetic myself, so make sure I get it right. Is 120. So this total cost is $320, and it's actually a per hour cost. So that's 120. And that's how we would, and then if we wanted 3 doctors, the 3 doctors, this cost clearly would go, the doctor's cost would go from 200 to 300, but this value of L would decrease, and in fact, just hypothetically, it decreases to 1.95 or 2. So then this then would go from 120 to 50. So that cost, in fact, would go up to 350. So it's still most cost effective with just these made up numbers to stay with 2 doctors. So another example, this is not in the textbook, nor was the information on the previous slide. So you'll want to be familiar with that. And last slide, again, just a summary of those formulas for the various operating characteristics. Again, I recommend that you do not use these, but that you use the Q macros whenever possible. If you use Q macros in order for me to check your work, I just need you to be sure to, on your paper or form or whatever you turn into D2L, be sure to tell me how many servers, tell me what you use, tell me what the lambda and the service rate, the arrival rates and the service rate, so I can go back and check your work if you use Q macros. All right. Next lesson, we're going to move on to inventory models. Again, as always, if you have any questions, don't hesitate to ask.